I suspect you remember this. As the syllabus tells you, each in-class quiz has a base value of 75 points. But as the syllabus also tells you, I purposely make available on every quiz exam a considerable quantity of earnable extra credit. That's because this stuff is tough, difficult, and I don't pull any punches. So for those of you who really are digesting this stuff, and I'm sure many of you will, this will give you the opportunity to show me just that. And for those of you who work hard, work diligently, but may take a while to get at appropriate digesting of this stuff, the possibility of earnable extra credit is my idea of putting the carrot out in front of your nose. Go get it. It's there. But keep in mind, I do not give extra credit. I give the opportunity to earn it. Big difference. Go get it. Now, more acid-base stuff, the likes of which will provide the remaining foundation for tomorrow's first in-class quiz. Definition. Many of you have heard this, but it's important. Percent ionization. Likely you've noticed this definition is on the information sheet. You don't need to memorize it, but you need to understand it so that you can use it appropriately. Concentration of derived species, like for acetic acid solution, acetate ion is clearly a derived species, if acetic acid is the only source of acetate ion in the system. Divided by the numerical label on the bottle, the initial molarity for the solute, times 100%, since we expressed it as a percent rather than a decimal fraction, but just a matter of definition. 10th molar acetic acid solution, we've already determined that the hydronium ion and acetate ion concentrations for this solution are each 1.3 times 10 to the minus 3. So percent ionization of acetic acid is 1.3 times 10 to the minus 3 by m divided by m sub I times 100%. 1.3%. Now, what have we recognized about degree or extent of ionization? As the acetic acid solution is made progressively more dilute, does the ionization extent increase, decrease, or stay the same? As you add more water, which of course is what you do when you dilute, you up the ratio of acetic acid molecules to you up the ratio of water molecules to acetic acid molecules. And for acetic acid to become hydronium ion and acetate ion, they have to bump into water molecules. And every one of these bump-in processes does not necessarily have the activation energy, will not necessarily convert to products. Be that as it may, if we up the ratio of water molecules to acetic acid molecules, have we not given a greater chance for acetic acid molecules to become the products, hydronium ion, acetate ion? So, what happens to extent or degree of ionization as we dilute? Increases. That's why one of the factors that percent ionization depends on is 1 over m sub I. The more dilute the solution, the greater the extent of ionization. Or you can say that degree or extent of ionization is inversely proportional to m sub I. It says the same thing. And of course, Ka or Kb. For two different weak acids at the same concentration, like 10th molar hydrogen sulfide ion in sodium hydrogen sulfate versus 10th molar acetic acid. The m sub I values are equal. Will the ionization extents for these acids be equal? Hell no. Which one will have ionized to the far greater extent? Hydrogen sulfate ion or acetic acid? Hydrogen sulfate ion. Why? It's a much stronger acid, got a much larger Ka value. Acid-base table tells you that. Because as we said, you surely have to know how to interpret the information on the acid-base table to make progress with this stuff. That's why quizzes and exams, we give you that table. You don't have to memorize it, but you have to know how to use it. Illustration. Question 1824. We're stating that acetic acid in a particular acetic acid solution is 13% ionized. Let's calculate M sub I for acetic acid. And associated with this, we'll provide this information. In 1,000th molar acetic acid solution, acetic acid is ionized 10%. That's the right molarity. I just want to be sure I wrote down the right molarity. No. I got the data wrong. Let's get this right. I thought it looked funny. There we go. Now we got it right. In the solution in question, or for the solution in question, the acetic acid is ionized 10%. With that, we give you the information that in 1,000th molar acetic acid is ionized 13%. Now, with this information, before we do any arithmetic, what can we say about M sub I for this solution compared to 0.0010? Is M sub I for this solution a bigger value or smaller value than this value? Bigger. More concentrated. That's why the ionization extent is smaller. All right? Now then, there's Ka acetic acid. Chemically, this is hydronium ion molarity times acetate ion molarity divided by acetic acid molarity, all equilibrium values. You know that. So let's go straight to this same equilibrium constant, but based on this information expressed algebraically. Based on this information, what is the hydronium ion concentration? What is the acetate ion concentration? What is it? X. I don't want any X's. You're given information which you must use to solve this puzzle. The label on the bottle is M sub I. What percentage of this label on the bottle is the hydronium ion concentration? What's it say? 10%. How do I write 10% as a decimal? 0.10. We'll take this as 2 sig figs. And the acetate ion concentration is? Same thing. So there's the numerator. What do we got in the denominator? The acetic acid molarity started out as M sub I. How much of it converted to products? 10%. How much of it's left? 90%. So what is the algebra representation for the equilibrium molarity of acetic acid? What is it? 0.90? Absolutely not, because that says you know the acetic acid molarity. 0.90. 0.90 what? M sub I. Then you got it. Don't forget this part. This hard to solve? Hell no. 0.0016 molar. Of course, m sub I divides from numerator and denominator, so you wind up with a first order equation. Solution is simple. Another variation of the theme. In this case, the variation of the theme on which we shall focus to solve this puzzle is the way I shall tell you to solve these puzzles. Now, I can't run around as an ethereal spirit when you work on quizzes and exams with a big club or laser gun or something like that, and overlook you as you work and say, "Zap! You're not doing this the way I told you." But if I could, I would. I guarantee. Because I'm telling you the best way. Now let's look at this best way. Okay so far? X squared over m sub I minus x, and for this solution m sub I is 1.0. Now let this thing talk to you arithmetically. By that I mean, for this case, do you or do you not believe that for this case, for this quadratic, 1.0 minus x is equal to 1.0? Because if 1.0 minus x is equal to 1.0, then x squared is 1.0, and the value for x is 1, which means this stuff is ionized 100%. And if it's ionized 100%, this k value means nothing. So for this case, does m sub I minus x, does 1.0 minus x equal 1.0? Hell no. Which means to solve this, you have to keep x in the denominator. Now, that immediately establishes this is a quadratic. So here's the sermon to which I was referring a moment ago. I know a whole bunch of you probably got calculators with the quadratic recipe programmed within. And I used to tell students years ago, before I learned better, that I'll let you use the quadratic recipe if you can derive it. If you can't derive it, sorry, permission denied. Is derivation of the quadratic formula difficult?
No.
Hell no, it's easy. How do you do it? What's the method?
Complete the square.
Complete the square, that's it. It's a simple derivation. But I'm not doing it that way, because that damn thing stands in the way of my appreciating and understanding chemistry, and I won't let anything do that. Not in the boundaries of this sacred place of learning. So the method I advocate, which is described in the notes, and if you've read the notes, you know what I'm talking about, is to solve these things by speculation on percent ionization. Because we know the percent ionization is somewhere between 0 and 100%. Nothing brilliant about that statement. And the percent ionization value, which until you learn better, because as you practice these things, you'll become more adept at letting these things talk to you. But now when you're just getting started, the first percent ionization test to apply is 50%. Why should I always try 50%? Let's see what this thing reduces to if I try 50% ionization. If I try 50% ionization, let's write this down. Try 50% ionization. I'll go over here for some scribbling room. Now watch out, this is really tough. What's 50% of 1.0? 0.50. Half of 1.0. That's really tough. Okay. So up top I'll have 0.50, and whenever I try 50%, then what I have in the denominator will compare how to m sub I. Be half of m sub I. It's really hard to solve, isn't it? Question. How does 0.50, which is what I get for this term, or this term if you prefer to call it that, if I try 50% ionization, how does that compare to Ka? Smaller than Ka, isn't it? Which means the true ionization extent for HA, the mythical acid in this solution, compares how to 50%? It's greater than 50%. I'm letting this thing talk to us arithmetically. Nothing fancy about this. Let's try 60%. What's that equal? I don't want any push buttons.
0.90.
0.90. It's 36 divided by 40. If you want to turn it into simpler values, which are equivalent. 0.90 is getting close to 1.0, isn't it? So I know the true ionization extent is close to, but a little bit bigger than 60%. There's the answer. You can do the arithmetic to prove it to yourself. What matters more than the answer is knowing how to get the answer. And as we'll oftentimes see, what matters more than the answer is knowing what the answer means. Why did we want to get this answer? I keep telling my 2045 folks, this is the part of the puzzle you're leaving out. They program you to push buttons on calculators and get answers. And I ask you to tell me what the answer means. Well, oh, what the hell that answer means? I was told to do it. I want to get the right circle bubbled on the damn answer sheet. The hell with that! That's not learning. You like these sermons? You think I mean them? You're damn right. I want you to understand. That's where it's at, and it's no place else. Not in the world of science. And not in the world of education. Understanding is where it's at. We make every effort to get there. Because that's where it's at. All right, let's try this one. Now notice we've already recognized from this problem, number 24, ionization extent, 1,000 molar acetic acid is 13%. Now this is 10,000 molar acetic acid. So before we do anything with this problem, just because we have this information available, always take advantage of what you know. What do we know about the ionization extent for acetic acid in this solution compared to 13%? Greater, isn't it? So that's telling us, do you expect this to equal m sub I? Do you expect 0.00010 minus x to equal 0.00010? Hell no. But we found that m sub I minus x is m sub I. Say, for example, for our 10th molar acetic acid. It's also true for 100th molar acetic acid, and it's also true for this 1,000th molar acetic acid, which you can prove to yourself if you do sit down with the paper, scratch paper and pencil and do the arithmetic. Let the arithmetic talk to you. So, for this solution, is m sub I minus x equal or is approximately the same as m sub I? Hell no. That means, like this problem, we have to treat this as a quadratic. We can't throw the x away in the denominator. But what have I just told you about ways to solve this? The way to solve it. Dictator Horvath's way to solve it. You know, the chief dingbat. That's me. What should we try first? 50% ionization. Okay, here we go. There it is. You write this stuff down just as fast as I can write it down. Even faster. Because you can write with a pencil on paper quicker than I can write with chalk on a chalkboard. At least I think you can. What's this equal? It's always going to equal half of m sub I, isn't it? That's a nice thing about this test. And for this problem, half of m sub I, which is 5.0 times 10 to the minus 5, compares how to Ka? Greater than Ka. So we haven't done anything fancy. And we know now for this solution, the extent of acetic acid ionization is greater than 13%, but less than 50%. We know that now. And we haven't done anything fancy. Let's try 30%. Here comes the real tough one. If 30% of m sub I goes away, how much of m sub I is left over? Ooh, that was hard. Now here comes the next tough one. 3 squared. 9. What's 9 divided by 7? Or put it more to the point, what's 9 divided by 7 compared to 1.8? 9 divided by 7 compared to 1.8. 9 divided by 7 is smaller, but is it a lot smaller? No. So we know we're getting close. Done. Now, of course, I wrote that down because I've already done this test. What I want you to do is to sit down with your pencil and paper and do the test. Prove that's right. It's not hard at all. Now's when the push-button calculator comes in handy. Because you'll have 3.4 times 10 to the minus 5 quantity squared up top, and 6.6 times 10 to the minus 5 in the denominator. So I'll let you. I'll gladly. I'll do it myself. I'll take 3.4 and square it and divide it by 6. Boom. Guess what I'm going to get? 1.8. How about that? All right, on we go. And I'll focus in brief about a very interesting aspect of acid-base chemistry, namely indicators and how they behave. You done any work in the lab with indicators? You're damn right. Both 45L and 46L. The first indicator whose chemistry we shall consider is arguably the indicator which is most commonly used when you want to get a handle on pH in water solution. The indicator's name is bronthymol blue. Its shorthand formula reference is HBTB, where the H in front means the acid form of the indicator, because all indicators are Bronsted-Lowry acids. And when they're deprotonated, then of course they're a conjugate base, therefore a Bronsted-Lowry base. Now these indicators have a very unique and important property. They have an electronic structure, which is, relatively speaking, low energy to the electronic structure compared to the electronic structure of most molecules. How do we recognize such, that statement is true? Did you learn in 2045? Because you talked about some of this stuff, but again, I don't know how much of it you applied. From what region of the spectrum of electromagnetic radiation do we need light to get electrons that belong to molecules to jump around? The fancy term is get excited. Move from low energy states to high energy states, or higher energy states. Did you hear about that stuff in 2045? When you want electrons to leave atoms, you generally need radiation from the X-ray region. Is X-ray low energy? Would you like to be exposed to a whole bunch of X-rays and become immediately fried? You don't want that, do you? But when materials have valence electron structures that are excitable by white light, visible light, what behavior is exhibited by the species? It's called color. How about that? Look at all the nice colors we have here. I got a yellow shirt, and over there orange, and kind of a violet purple, blue and orange. Ooh, shiny, sparkly green up there. They got all kind of neat colors. That's the way these indicators behave. They have valence electron structures, which are large, relatively speaking, and conjugated. Ho! Did you hear that fancy word in 2045? Conjugated electron structures? I'm just asking if you heard the word. In 2045, did you at any time look at the valence electron structure for benzene? In talking, for example, about RESONANC, yeah, resonance, okay. The resonance structures are conjugated. How about that? We'll talk more about that later, but not now. Just another term, but an important term. Here's the colorimetric behavior for HBTB. Now, the most common pH range that's analyzed in water solution is 0 to 14. Can we have pHs lower than 0? Yeah. You got hydronium ion concentration bigger than 1, pH is a negative number. Can we have pHs above 14? Yeah. If the hydroxide ion molarity is greater than 1, the pH is bigger than 14. But most commonly, we're dealing with solutions that are less concentrated than 1 molar, either hydronium ion or hydroxide ion. And HBTB is the most commonly used indicator in pH analysis for water solutions because it hits at the middle of this range. If you want to know straight away whether or not an unknown solute in water solvent behaves as a Bronsted acid, Bronsted base, or neither, because it hasn't got any acid or base properties that amount to anything. You make a water solution of this stuff at fairly high molarity and treat the water solution with HBTB. If you see this, stuff's not acidic or basic. Now, for the deionized water we use in laboratory, which by now you folks have a reasonable degree of familiarity with. When you're in 46 laboratory, what's the first investigation you should make at the start of each and every laboratory class? I want to know if your TA told you this. I want to know if I have to get the TAs all together in a big group so I can horsewhip them all at once. Whap, 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 whap. Why the hell don't your students know that the first thing they should start with at every laboratory class is to test the pH of the deionized water? Because all the damn chemistry they're doing is in that stuff. How about that? Well, now you heard it. From the horse's mouth. And watch out, I'm a big horse. I hope this is the appropriate end of the horse speaking to you. Our lab deionized water usually runs about pH 6, presumably because of absorbed CO2 from the atmosphere. Or because you took a straw, put the straw in the water and bubbled your breath through there. At pH 6.0 or lower, we see a yellow color. pH 8.0 above, we see a distinct blue color. Now, you played with watercolors with it when you were a kid, didn't you? I hope you did something besides fool around with that damn computer. I mean it. Smart parents, my opinion, my humble opinion, which is any damn thing but humble. If I still had little kids in my house, I'd say 1 hour a day max with the computer, that's it. The rest of the time you're going to do something, like go outside and play baseball or tag or something and run around and get some exercise. And if I ever see any of my kids with one of these damn push-button games where you're playing ping pong with a button, I'm smashing that with my sledgehammer right now. Hell with that junk. I mean it. Body corruption. When I mix equal quantities of yellow with blue, what do I get? Green. Ha ha ha. So when I make equal quantities of that component of this stuff which is yellow with that component of this stuff which is blue, I get this distinct green color. So we're going to look at this equilibrium, because this represents the conversion of HBTB by reaction with water to make hydronium minus BTB minus, and ask the question, is this the yellow stuff or the blue stuff? Is this the yellow stuff or the blue stuff? If this is the yellow stuff, then this is the blue stuff. But if this is the blue stuff, then that's the yellow stuff. When I have these things mixed in equal mole quantities, I get green. Just like the little kid playing with the watercolors. I hope you did that. I did. It was fun. Slop, slurp, slop. Half of the colors on me. Who cares? It's watercolors. They wash out. Make pictures. A little flower. Then you write mom on there. She says, oh, that's so nice. Right? Which one is yellow? Which one is blue? This information allows you to decide. All right, we'll have a vote. HBTB, the protonated form, HBTB is yellow. Just about everybody voted right, so I won't ask for any more votes. That's good. Hey, this information tells you, as you make the system progressively more basic or less acidic, however you wish to say it, you go from yellow to green to blue. And as I make a system more basic, do I extract protons from an acid or do I give protons to the acid? As I make the system more basic, do I extract protons or give protons? Extract. Hey, bases are proton robbers. And I make this thing more basic, I'm getting to a blue color. So I now know this blue, this yellow. Now more fun. From the information we have on the board, no other information is needed. To one significant figure, I want to know the Ka value for HBTB. To one sig fig, based on the information on the board. And your understanding and appreciation of acid-base chemistry, which at this point I fully expect. To one sig fig, I want to know Ka for HBTB. I'm listening.
1/10
Right. How many are mystified by this value? If you know where it comes from, then you got your hand down, so everybody knows where it comes from. Is that correct? Because this kind of stuff is on tomorrow's quiz. You know how to do this? Well, how come I'm not seeing any hands? Don't be bashful and shy. To hell with that. That doesn't get you any place. When you don't know, say so. It's not announcing that you're proud of not knowing, but at least it's announcing that you are of a mind to learn. Okay so far? Nothing fancy about this. We've already written KAs all over the place. A number of times. Now tell me, at a pH of 7.0 for this indicator, what color do I observe? Green. And how do I get the green? By having HBTB and BTB minus present in equal concentration. How about that? So at green, these molarities are equal. And at green, where I have a pH of 7.0, the hydronium ion concentration is 1 times 10 to the minus 7. 1 sig fig, and there's KAHBTB to 1 sig fig. Done. Statement. When you have the boundary pHs for an indicator, for this indicator, 6.0 and 8.0. The pHs below which and above which no further color changes are observed. All you need to do is to take those boundary pHs, add them up and divide by 2, and that'll give you the pH when the indicator is ionized to what extent? What extent? 50%! And when it's ionized 50%, you've got a mix of the colors. Equimolar mix of the colors, blue and yellow. And that is the pH that gives you the hydronium ion concentration, which is equal to Ka for the indicator. We just showed that. Now, let's go to question 1829. Aha! Now we're talking about one of my favorite hypothetical indicators. Gainesville green. Gainesville green shows a behavior which is rather similar to HBTB, but it does its thing in a somewhat lower pH range. And Gainesville green, this hypothetical indicator, shows a behavior that's very similar to Brome-Kressel green, which is an indicator you have available for use in 46 laboratory. Tell me, is Gainesville green a stronger acid or a weaker acid than bromethymol blue? Stronger. Stronger by what factor? 10 times stronger. You know that already. Now then, I'm going to take a solution of a hypothetical acid, 1 molar, 100 milliliters. There's the hypothetical acid. HJ. That's Horvath James. Just in case you didn't know. And I'm going to treat this solution with a drop or two of indicator Gainesville green and with 1D HGG ind for indicator, I get a green color. Q. Which acid is stronger? HGG or HJ, and by what factor? We have all the information necessary to answer this question. Which acid is stronger and by what factor? All right, we'll start with a vote. The stronger acid is HGG. The stronger acid is HJ. The stronger acid is I don't know because I didn't vote. I made 3 requests and I still know there's a bunch of hands that have not yet gone up. Those people have been caught by my video. And on your quiz tomorrow, like you see on the web, you get this pop-up note. The pop-up is going to say, you owe me 1 million points. Let me see you get that back. Not only is HGG stronger than HJ, it's one hell of a lot stronger. It's 1,000,000 times stronger. How about that statement? Are you mystified by this assertion? Yes. Well, then let's write some chemistry. Because you know, I think, if I want to compare the strengths quantitatively of 2 or more acids, I have to have their Ka values and take the ratio of the Ka values, right? That's the handle I have, the quantitative handle I have on acid strength. Kb for a base, Ka for an acid. Does it look okay so far? Nothing fancy. We've done what we've done many times already before. We've done it again. Did it again. For this HJ treated solution, what is the pH? What's the hydronium ion concentration? 1 times 10 to the minus 6. What's a J minus concentration? 1 times 10 to the minus 6. Is it not? We said we took this solution, treated it with a drop of indicator, got a green color. Green color is 6.0 pH. So that's hydronium ion concentration and a J minus concentration, because in this solution the only solute of consequence is HJ. And HJ plus water, hydronium ion J minus. So for this solution, hydronium ion molarity, J minus molarity be the same. So that's 1 times 10 to the minus 6. Quantity squared. What have I got in the denominator? 1. There's Ka for HJ. What's Ka for HGG? Hydronium ion molarity at this pH? At this pH? 1 times 10 to the minus 6. So KaHGG is 1 times 10 to the minus 6, which is 1,000,000 times bigger than this. That's why I told you folks who didn't participate that you owe me 1,000,000 points. There it is. Ha ha ha. You see to what extent HJ is ionized in this solution? Damn near nothing. It's 1 times 10 to the minus 6 over 1 times 100%. HJ is ionized 1 times 10 to the minus 4%. I think it's fair to say that practically speaking that stuff ain't ionized at all. We'll pick it up from this point next time.